Welcome back. So today we're going to see another example of Lagrange multipliers, and this time we're going to have a look at a more abstract setting in an actual economic application. Specifically, we are going to take a look at a model of purchase under budget constraints. So our example is purchase under budget constraints. So the model is the following. We have a number of products. We just number those products from 1 to n. Those products have prices. And those prices will be denoted by alpha 1 to alpha n. And that'll give us a price vector. The price vector will denote by A. So A is just the vector alpha 1 to alpha n. Then, of course, we have a budget. We call that budget beta. Beta is a real number greater than 0. So that's the budget we can spend. And we have a desired purchase. So we'd like to purchase x1 bar units of good 1, x2 bar units of good 2, and so on, up to xn bar units of good n. Problem is, we cannot afford this desired purchase. So, in other words, the sum of the alpha I xi bar, I from 1 to n, so the price that we have to pay for our desired purchase, that is greater than the budget that we have. By the way, we can write this as a scalar product of A and the vector x bar. So this is greater than the budget. So we cannot possibly afford the desired purchase. And what we'd like to do is we'd like to find a purchase decision, a vector x star, that is close to this desired purchase x bar, but that satisfies the budget constraints. So the question is, what do we have to give up to still be close to what we want, but to be able to afford our purchase? Okay, so find a vector x star that is close to x bar, but that satisfies the budget constraint. In other words, more formally, what we want to do is we want to minimize the difference between the vectors x star and x bar. So we want to solve the following optimization problem. We want to minimize a function f of x that is defined as the norm of x minus x bar, and x star is then going to be the optimal solution that we want. And to make things a little easier, we're going to take the square of that norm. Whether we minimize the norm or the square of that norm doesn't really matter for the minimizers, but it makes things a little easier to, in terms of notation. We don't have to deal with square roots that much. Okay, and there's our constraint subject to the budget constraint, and the budget constraint is the prices times the purchase, so A transpose X. That's what we have to pay for our purchase decision X, and that price should be equal to the budget that we have available, so that's equal to beta. Okay, and that means, well, our function f, we've given that right here. So f of v is a function from r to the n mapping to r, and here's our function h. H also takes x as the input parameter, and also maps to the real numbers with h of x is equal to A transpose X minus beta. And that function should be set to 0 in the constraints. Okay, so this is our actual optimization problem. And again, let's have a look at the Lagrange function. So L of x and the Lagrange multiplier set. So the output of that function h is one-dimensional. That means we only need one real Lagrange multiplier. We call that one set. So this is f of x plus set times h of x, as you know. And specifically, here what we have is the norm of x minus x bar squared plus z times A transpose x minus beta. Okay, and to make that a little more clear even, we could also write this in terms of the xi, so that the differentiation step becomes a little more obvious. So this x minus x bar norm, this is the same thing as the sum over the xi minus x bar I squared, like this. And this latter part here, that's the same thing as z times the sum of the ai xi minus beta I from 1 to n. Okay, so that should make differentiation a little easier. So what do we get if we differentiate that function? Let's see. We want to differentiate our L of x and z. What we get by differentiating with respect to the variables x1, x2, x3, and so on up to xn. In this first expression here, each of the variables is containing exactly one summand, so all the others will vanish, and what we get, what remains, is simply a 2 times x1 minus x1 bar, 2 times x2 minus x2 bar, and so on, up to 2 times xn minus xn bar. So that's this first part here. In the second part, what we get is again a sum over all the ai xi. And you can again see each xi is containing exactly one of those summands, and differentiating those with respect to xi gives us the ai term here. And of course we still have to multiply by z. So what we get here is plus z times a1 and so on, z times an. And finally we have to differentiate with respect to z. Z is not appearing in that first part, and it's just appearing here once, so what we get is this last part. And of course you could also just formulate that as the constraint has to hold, so the solution has to be feasible. But we could easily integrate that here as saying, well, that sum of the ai xi minus beta, that has to be 0. Okay? So the condition here is all of this has to be equal to 0. Okay? Or, in other words, if we formulate this a little more concisely as a vector, we get this condition here that 2 times x minus x bar, that's the first part here, so this vector here, that's 2 times x minus x bar, plus z times a, that is this second part here, z times a. Remember, z is just a real number here. That has to be 0. And at the same time, this constraint here has to hold, and that is just a transposed x equals beta. Okay, so this is again the necessary conditions for an optimum, for a local optimum. So all that remains is, well, we have to solve that condition. That's not that hard, actually. Let's try to solve the first constraint for x first. So what we get is 2x minus 2x bar equals minus ZA. And of course, that's the same thing as if we solve that for x. Then we get x equals x bar minus Z over 2 times A, like this. Okay, remember x bar is a constant, that's part of the input. A is also part of the input. So we have expressed x in terms of the input and z. And now we can continue to substitute that into the second constraint. So from ATX equals beta, we get, by substituting that into this constraint here, we get A transposed x bar minus Z over 2A equals beta. And thus we have an equation where only Z is the unknown contained in that equation. So we can solve that for Z. So that means if we want to do that, let's see, we get minus Z over 2 A transposed A plus A transposed x bar equals beta. And if we are going to solve that for Z, then what we get is Z is 2 A transposed x bar minus beta, and then we have to divide over this ATA. And remember, ATA, that's a real number. Yeah, so we can divide over that. It's not a vector anymore. It's a scalar product of A with itself, or in other words, the norm of A squared. Okay, so actually looks like this. And of course, it only holds if A is actually not 0. So, but if all the prices are 0, then there is no way we can actually reach our budget. So that's not a feasible assumption in that case. Okay, so we can safely assume that the prices are not all equal to 0. So that's the set that we get. Yeah, and of course, once we have solved for that, we could substitute this into the other equation that we get. Substitute Z into x equals x bar minus z over 2a. And then we simply get x equals x bar minus the 2 cancels out here. So remember, we take this expression here and substitute it here. So the 2 cancels out, and what we get is a transpose x bar minus beta over the norm of a squared times a. Okay, so very unsurprisingly, this expression for the optimal x depends on the price vector. We finally have that solution. So this is our x vector. The corresponding set was above. This is the x vector that we get. That's the corresponding value of the Lagrange multiplier set. And we are actually able to compute a general solution for that setting. So once you have the price vector A, once you have the desired purchase vector x bar and the budget beta, you can then solve for x and obtain a setting for the purchase variables that you can actually realize with your given budget, and that is close to your purchase desire in the first place. Okay, that concludes this example. And in the next videos, we're going to extend that setting into inequality constraints, because obviously here we set a condition that spends the whole budget, and that is usually not necessary. What you want to do is stay within budget. So less or equal would be the more natural equation. Of course, you'll usually spend the whole budget if you can, because that will help you get your objective function to a better value. But it's not strictly necessary, and it seems a little unnatural to model it that way. And of course, there are settings where actual inequality may occur, and we'll see examples for those. So that's the next thing that we're going to talk about, extending that setting to inequality constraints. I'll see you in one of the next videos then, and goodbye.